All right, now we're going to try to incorporate our counting principles into calculating probabilities. Looking at our fundamental counting principle, the formulas for combinations and permutations as well. And so to do this, a real interesting example, a lot of them I'm going to do are card-based or dice or coin flip, just because they're kind of simple, basic. You can even do them right here as an experiment, which I tried in a previous video, and it was a little bit weird. But so I'm going to try this one. I'm going to play Texas Hold'em poker. If you've ever played poker before, Texas Hold'em is where you get two cards in your hand. Everybody gets two cards that you get to see, but no one else does. And then they have some shared cards out on the table. They flip three over, and everybody shares those three. You make a hand with the best five possible cards. So you get three showing, and then everybody bets, and then you get one more showing that everybody bets, and you get one more showing. So there's 7 cards out there, and you make the best 5, or you make a hand with the best 5 cards. I think I'm saying that right. Anyway, and so that's Texas Hold'em. Well, a really nice hand would be what we call pocket aces. Pocket anything is where the 2 cards in your hand that you see are the same. So a pair of aces, or did I say aces? I want kings. My head's in the way. Kings, pocket kings. Pocket ace is great too. That's probably better. Well, I don't know. Some might think the kings are better. You have more options there, but aces are higher. But anyway, so I'm just going with kings. It doesn't matter. It's arbitrary which one it is. It could be pocket 2. It's the same probability. So Texas Hold'em poker, 2 cards. Seeing what the probability of getting pocket kings is. All right. So how do we figure that out? Well, first you have to figure out how many ways you can get pocket kings, and how many different hands there are total, and then divide them. Okay, so what's interesting here is that it doesn't matter what order you get them dealt to you. So the order doesn't matter. If order doesn't matter, we're looking at combinations, not permutations. So this is a combination problem. And you want basically the number of ways of getting kings, 2 kings. Well, how many kings are there? There are 4 in the deck. You want to get 2 of them. And it doesn't matter the order in which they come. So we're doing a combination of 4, choose 2. Okay, so the number of pocket king hands is going to be 4, choose 2. The total number of possible hands in a Texas Hold'em game, at least the 2 cards that you're dealt, total number of possible hands. Well, that's going to be, there's 52 cards, choose 2. 52, choose 2, right? Again, the order in which you get those cards does not matter. And so the probability of event, we'll call it event E, where E is pocket kings, or you could say, the set of all possible ways of getting kings. So it's the cardinality of that set. Well, that is the 4, choose 2, which is, we'll write that out. 4, choose 2 divided by the number of possible hands total, which is the sample space, 52, choose 2. And so when I calculate this out, it's going to be a fraction on top, fraction on the bottom. We can do a bunch of canceling. 4, choose 2 is 4 factorial over 2 factorial, 2 factorial, right? The difference and the r. So n factorial over the difference factorial and r factorial, both on the bottom. And then 52, choose 2 is going to be 52 factorial over the difference, which is 50 factorial, times 2 factorial. Okay, so those are my 2 calculations, my 2 combinations. And then I have to just simplify those. Well, the top one, maybe I'll write that as, actually I could do quite a bit of canceling right there. Well, I don't know, maybe we'll just do it this way. So that's 4, times 3 times 2 factorial, and the bottom is a 2 factorial, and so right, 4 factorial is 4 times 3 times 2 times 1, that's 2 times 1, 2 factorial is another 2 times 1, just kind of expanding this out so I can do some canceling, right? The bottom is 52 factorial, well that's actually 52 times 51 times 50 factorial, right? You got the rest of them all encompassed in the 50. And then you got another 50 factorial, which is nice. And a 2 factorial, which is just 2 times 1 again. And so, how do I do this? Simplifying. Well, the 50 factorials disappear. That's a lot of factors gone. And so, 4 over 2 is 2, so that's 2 times 3 is 6. So my numerator is 6. 6 is the number of ways to get pocket kings. The number of pocket kings hands out there. King of hearts with king of spade, king of heart with king of club, and so forth. All those combinations, only 6 of them. And then if you get the total number of hands, if I divide out the 2 and the 52, that's 26. 26 times 51, I actually don't know that, but I could probably figure it out quickly, but I don't want to. 26 times 51 is 1326. Huh, I was thinking it was more than that. So there's only 1,326 total possible hands, at least the first 2 cards you get anyway. After that, when you start getting the other 5 cards out there, the shared cards, that number increases, but I'm just looking for the 2 cards dealt. And then I can reduce that. Does it divide evenly? No, but it's just divisible by 2. If I reduce it down, they're both divisible by 2. That'd be 3 over 663. Oh, it is. Oh, there's a 3 in there. There's a 3 hiding, so divide that by 3. And it's 1 over 221. Okay. So the probability then of getting pocket kings is 1 out of 221. So if you were to play, no, this is the theoretical probability, not the empirical, theoretical. Theoretically, 1 out of every 221 hands is pocket kings. Now in practice, if you're sitting, if you're playing with some friends one night and you only play, 40 or 50 hands of poker and you end up getting pocket kings twice, that's rare. It could happen because that's the empirical probability, would be the 2 out of whatever you had. But 1 out of 221 is the theoretical probability, okay? Now that is a decimal. 1 divided by 221 is about 0.0045. So approximately 0.0045, or about a 0.45% chance. So it's under a 0.5% chance of getting pocket king. So it's a small chance of under 0.5%. I don't know how to better say that or better quantify that, but now let's say, for example, I change this up a little bit. Let's just say I wanted pocket pairs. It could be any pair, kings, aces, 2s, 3s, 9s, jacks, anything, doesn't matter. How do I make that calculation? Well, to do that, so if I want the new E, let's actually, instead of making it event E, let's make it event F. Just use a different letter here. And let's call that pocket pairs. Well, what's nice about this example is that there are the same number of ways to get pocket 2s and pocket 3s and pocket kings and pocket jacks, everything. All the different pocket pairs are equally probabilistic, right? Yeah, I don't know if the word is weird, but that concept makes sense. And so the probability of getting pocket 2s would be 0.45%. Probability of getting pocket 10s is 0.45%. And so when you total all that up, you look at pocket pairs, the probability then, you add up the number of ways to get each one. 6 different ways to get each pair, or to get each number as a pair. And so what you end up with, P of E, is actually 13 of these, right? So you add up all the sixes, right? So there's 6 different ways to get pocket twos, 6 different ways to get pocket threes, 6 different ways to get pocket fours, and so forth. And so you add them all up, you get 13 possible combinations. So 13 times the 6, right? 6 plus 6 plus 6, 13 times. Over the same 1326, okay? And then that probability works out to be 13 over 221. And I don't think 13 divides 221. Oh, it does. No way. Oh, that's not a fluke. Oh, that's because 26 is one of the factors of 221. Or no, it's not. It's one of the factors of this, which means that I divide it over 2. Yeah, that works. Oh my goodness. Okay, that's cool. So that's actually a 1 in 17 chance. If you divide out 13 on both of those. So it's a 1 in 17 chance. And 1 divided by 17 is approximately 0.059 or 5.9%. So you have a 5.9% chance of getting a pocket pair on any given hand. Now, I feel like I could play all night, play 40 or 50 hands of poker and never seem to get a pocket pair. I don't know why that is, but I always blame it on not getting good hands, but I must lose money because I'm just not good at it. I don't know. Anyway, so 5.9% chance of getting a pocket pair on any given hand, which is about 1 in 17. So out of every 17 hands, you would think theoretically, the theoretical probability is you'd get 1 pocket pair out of every 17 hands. Now, the empirical probability is you play however many hands, 40 hands one night, and maybe you got 5 different 5 pocket pairs during the night. 5 out of 40 is 1/8, and so you have a slightly different probability during that given night. But in the long run, if you were to play 40 hands on 60 different nights or something throughout the course of your lifetime, this probability, the empirical probability would approach this theoretical probability, be a lot closer. Some days it'd be more, some days it'd be less, but in the end you would approach that one. Okay, so that gives you an idea of how to use combinations to calculate probabilities. So you calculate the number of combinations for the event, divide it by the total number of combinations possible, and that gives you the probability.